We are discussing greedy strategies for algorithm design. Okay. The main principle is to somehow construct a solution to your problem piece by piece. Okay. We saw two examples last time. Let's quickly sort of revise the main lessons that we learned. Okay. So, greedy strategies for algorithm design is being reviewed. The main point is you somehow construct the solution piece by piece. Okay. So, two things are important. One is what is the next piece of your solution. Okay, that is the crucial question that you have to answer. And once you answer this question, you just put it around in a loop and you get your algorithm. Okay. The other thing we saw, especially with the second problem, was to find the input was a set of intervals, and the output was maximum number of intervals that do not overlap with each other. Okay, pairwise they do not overlap with each other. Now, we saw that two obvious strategies for this problem failed. One was to pick smallest interval, or the strategy of picking an interval which overlapped with the smallest number of other intervals. Okay, both of these seem to be natural strategies to consider, and they fail. The strategy that worked, we saw last time, was to pick first the interval that ends first. Okay, to pick an interval that ends first, remove the intervals that overlap with this, okay, and then you recurse on the rest. Again, you pick an interval that ends first, and so on. Yeah, so the sort of moral of that story was obvious strategies may not work. Okay. Well, what is obvious to one may not be obvious to the other, but certain obvious strategies which appear obvious to most normal human beings may turn out not to work. Okay. So, the point that I want to stress is a proof of correctness is important. If you come up with a greedy strategy, okay, you need to argue logically that this strategy works. Okay. So, let me write this down, this is important. So, hence a proof of correctness is necessary and important, okay, because obvious things do not work. If you are giving an obvious solution to a problem, then you better say that prove that this obvious solution is indeed correct. Okay, so this is important. There are usually two ways of writing a proof for these greedy strategies. One is induction. Okay, since you are constructing these solutions piece by piece, you find the first piece, okay, argue that this is correct, and then your proof of correctness usually works by induction on the rest of the input. So, you argue that on the rest of the input your strategy by induction works, okay, and added to the first thing that you picked, it gives you an optimum solution. Okay, this is what we followed yesterday, right? Now, there is one more way of writing this which is also quite popular, which I will call exchange. So, this is proof by the exchange technique. Okay, this is very similar to the exchange trick that I have been mentioning throughout, and we will look at it in a bit more detail. Okay. What we will do is take up the second problem that we looked at and actually write a proof, derive a proof by using this exchange business, just to get it into our heads. Okay. Okay, so here is how the proof by exchange works. Okay, let us review the algorithm first. It says pick, this is among the intervals that remain, the interval that ends first, okay. Discard intervals that overlap with this interval, okay, and the whole thing is in a loop. Okay, this whole thing is in a loop, and you are done when you've discarded all the intervals. When you have an empty set, you start out with a set of intervals, do this in a loop till you don't have intervals to deal with. Okay. Now this was the algorithm. We know that this works. Let's now prove using this sort of exchange trick that this works. Okay. The proof is actually logically the same, only it's written a bit differently. Okay. So how does this work? Okay, suppose, so here is a proof of correctness. Okay, there is a second proof of correctness. Okay, suppose the algorithm picked intervals, let's say I1, I2, I3, so on up to Ik. Okay, let's also suppose that they are sorted, say sorted by, doesn't matter whether it's finishing times or finishing times. Well, if they are sorted by finishing times, they are also sorted by starting times, because these intervals are disjoint. Okay, so the intervals, they look like this. Let's say this is I1, that's I2, I3, so on, that's Ik. So the intervals are disjoint, so sorting by finishing times and starting times, it's the same thing. Okay. Suppose the algorithm picked these intervals I1, I2, I3 up to Ik. Okay. Now we have to somehow show that there is an optimum solution which also picks these intervals. If this is indeed true, okay, if there is an optimum solution which has I1, I2, I3 up to Ik, then we are done, because every other interval in the input must overlap with at least one of these inputs. Okay, the way the algorithm works, it picks an interval, throws out the intervals which overlap with this. Okay, and finally we have an empty set. So there is a set of intervals that we picked, that's I1 through Ik. There is a set, the rest of it has been discarded because they overlapped with one of these intervals, right? So if any optimum solution has I1, I2 to Ik in it, okay, then this is it. The optimum must have size k, right? So let's pick. So this is what we need to show, that an optimum. This is an optimum solution, right? Suppose this is not so. Okay, there is no optimum which has I1, I2 I3 up to Ik. Okay, then pick the optimum solution which has maximum number of initial intervals in common with this, with what the algorithm picked. Okay, so let me write this down. So suppose, so the claim that we want to make is there is an optimum solution containing I1, I2 and so on up to Ik. Well, in this case we just saw that if it contains these, it must be exactly this, in which case this is optimum. Okay. So if we prove this claim, we are done. So the proof is by contradiction. Okay, proof of the claim by contradiction. Okay, so we start off by saying suppose not, which means suppose the statement is false, there is no optimum solution which contains I1, I2 all the way up to Ik. Okay, that is what this means. So, then pick an optimum solution which has the maximum number of initial solutions, initial intervals in common with I1 up to Ik. Okay, what do I mean? So, there may be some optimum solutions which contain I1 which do not contain I1, there may be some which contain I1 and I2, okay, but not I3. There may be some which contain I1, I2, I3 all the way up to I17 but not I18 and so on. Okay. So, of all these optimum solutions, pick one so that the maximum number of initial intervals are in this optimum solution. Okay. So, suppose then this optimum solution has I1, I2, I3 up to Ij say. Okay. So, this has I1, I2 up to Ij, okay, but not Ij plus 1. Okay. So, this says that there is an optimum solution which has I1, I2 up to Ij and no optimum solution has Ij plus 1. Okay. When I look at all these optimum solutions, there could be many, none of them has Ij plus 1 in them, okay, but there is one which has I1, I2 up to Ij. So, let us fix this and look at it. Okay. Now, since it has I1 through Ij, okay, since it has I1 through Ij, every interval which overlaps with these is not present in the optimum. Okay. So, every interval which overlaps with I1, I2 to Ij is not in the optimum present in this optimum, right. In fact, it is not present even in the algorithm sense. So, let us look at Ij plus 1. Okay. So, yeah, so here is the optimum, it has I1, I2 up to Ij, okay. Then it has some other interval, call it interval k, okay. The j plus 1th interval in the optimum is k. So, let the j plus 1th interval in the solution be k. So, it looks like this and then there are others. Okay, this is how the optimum looks. Now, Ij plus, so k looks like this, okay, this is k. Now, the claim is that Ij plus 1, okay, ends before the ending time of k. Okay. So, this is the crucial, let me write this down. The ending time of I j plus 1, this is what the algorithm picked, is less than or equal to the ending time of this interval k. Okay. The ending time of Ij plus 1 is less than or equal to ending time of k. Well, which means Ij plus 1 Okay, it must look like this. I have k, okay, this is k, and ij plus 1 should look like this. It could be the same as k, but it's certainly less than equal to this, and ij sits like this, and so on. Okay, this is the picture that we have. Okay, now you notice that I can put ij plus 1 in to this optimum and remove k. Okay, so look at this picture. So in this picture, the optimum has other intervals, k and so on. This is what the optimum looks like. I can insert ij plus 1. The only other interval it intersects with is k. Okay, so I can insert ij plus 1 and I can remove k. Okay, because this is the way the algorithm picked ij plus 1, and it's because you pick an interval with the smallest ending time. Okay, that's the reason the ending time of ij plus 1 is smaller than or equal to ending time of k. So I can insert ij plus 1, remove k, and this is a contradiction because now I have an optimum of the same size which has ij plus 1, and that's a contradiction. Okay, let me just write this down. Okay, so hence replacing k with ij plus 1 gives yet another optimum solution. Okay, it gives yet another optimum solution which contains I1, I2 up to ij plus 1 now, which is a contradiction. Okay, end of proof. That's it. So this is well, a proof by contradiction, a proof by this exchange technique, that somehow you exchange what the optimum has with what the algorithm constructed. As I said earlier, you could write the same proof by induction too. Okay, that's another way of writing the same proof, and you can pick whichever way you want to write, whichever way you like. Okay, so this was the previous example. So let's look at some more problems. Okay, the idea is to give you a flavor of the kinds of some kinds of algorithms, problems and algorithms. Some of them are easy, and you follow your nose and you get exactly what you want. Some of them are, well, like this one, they may be slightly more non-trivial. Okay, so this is just to give you a feel of the kinds of things that you can do with greedy algorithms. Okay, so here's the next one. The input is a set of intervals as the previous case. Okay, the output is to partition this set into a minimum number of paths such that in each part you only have non-overlapping intervals. Okay, so this is similar, the input is similar. So let's go back to this scheduling problem that we had previously. Previously you had, these set of intervals. Each interval is associated with a user. So the user gives you an interval where she wants to work, right? And your job is to sort of, satisfy as many users as possible. Only 2 users cannot work on this machine at the same time. Okay, so the intervals should not overlap. Now you still want to schedule them, okay, only you have more machines. You have many machines, okay. On the same machine you cannot schedule two users at the same time, okay. So I cannot schedule two intervals which overlap on the same machine, and I want to minimize the number of machines, okay. So users come with these requirements, which is an interval. Each user comes with an interval. You have a number of machines, you want to minimize the number of machines that you use, okay. So which means I have to tell for each user which machine he or she should sit on, right, and it should be such that for each machine two users whose times overlap should not sit on the same machine, okay. So for if I look at the schedule for one machine, it should be, the interval should be non-overlapping, okay, or disjoint. So this is the problem, okay. In an abstract way, the input is a set of intervals and the output is to partition this set of intervals into minimum number of parts, okay. These are each part, think of each part as a processor. Within each part I must only have non-overlapping intervals, okay. In other words, within each part I cannot have two intervals that overlap. So this is the problem that we would like to solve, okay. So how does one go ahead doing this? Again, the sort of, since we are discussing greedy techniques, okay, I guess one would like to do it by you just keep partitioning these intervals, putting them in different parts one by one till you are done, right. So look at these intervals in some order, say, okay, and you decide which part or which processor that person is going to sit on. Again, the crucial question is, which order do you look at the intervals, okay, in which order do you look at intervals? You can try ending times too. I mean, since the previous problem, we looked at intervals based on ending times, okay. The first interval that ended first was scheduled on, was looked at first, and then the interval that ended next was looked at next, and so on, okay. This is the order in which we looked at intervals. Does this work? Well, I'll let you figure out if this works, okay. So that's an exercise for you. Just see if you can look at intervals based on ending times, okay. When you get a new interval, put it on one of these processors, okay. Which processor? Well, you'll have to decide that. The sort of greedy way of putting these intervals onto processors is order these processors 1, 2, 3, 4, 5, 6, 7 and so on, okay. And when you get an interval, put it on the first processor that you can, okay. So if there is some interval on the first processor to which this overlaps, then I do not put it in, and so on. So I just keep going 1, 2, 3, 4, and the first place where I can put it, I put it in, okay. With this sort of greedy backdrop, supposing you look at intervals by finishing times, this is what I want to check, whether this will give you an optimum solution. Well, we'll look at it differently, okay. We'll first sort by starting times, okay. We'll sort intervals by starting times. We consider the input in this order, okay. And what we'll do is this: when I come to the ith interval, I order these groups 1, 2, 3, 4, 5, okay. I check whether I can put it into the first group. If I can, well and good. If not, I look at the second group and so on. So I put it into the first group where I can, okay. This is the algorithm. So let me write this down, and then we'll see why, if at all, this is optimum, okay. There doesn't seem to be any, I mean, on the top, on sort of on the face of it, there is no real intuition as of now guiding me, right? I mean, why should I choose intervals? Why should I order them by the starting times? I could have ordered them by the ending times. I could have ordered them by sizes or any other parameter that you may have. Okay. But well, we'll do it by starting times and we'll see what happens. Okay. Okay. So so here's the algorithm. Okay. Consider the intervals the order specified by increasing starting times. Okay. And so for an interval I, okay, let's say I t, okay, this is the tth interval when considered in this order. Put it in the first, okay, put it in the first group or part that you can. Okay. So you consider intervals in this order, and when I look at an interval it, put it into the first part that you can, which means in the first part in which it does not have a it does not have an overlapping interval. Okay, if I put it in part L, say, that means when I look at part 1, part 2, part 3 up to part L minus 1, in all these there is some interval which overlaps with IT. Okay. Yeah, so this is the algorithm. And why does this work? Does this work? Well, it does. The algorithm does work, and let's in fact prove that this works. Okay. Okay. So, well, you run the algorithm on a set of inputs, right? So initially, the first interval goes into the first part. The second interval, if it does not overlap with the first one, okay, goes into the first part. If it does overlap, it goes into the second part, and so on. So you just sort of scan. Your objective is somehow to figure out what happens to the number of parts, right? You are minimizing the number of parts. Okay. So supposing the number of parts were k, the algorithm produced k parts. It was broken up into k parts. Okay. Somehow we need to argue, I mean, if it is in fact optimum, that any algorithm will produce these k parts, right? So let's see why. Okay, so let's say supposing the algorithm partition a set of intervals into k parts. Somehow we have to now argue that any algorithm on this same set of inputs would use k parts. Why should this be true? Well, let's look at small values of k. Okay, so often the other sort of trick which is never sort of mentioned in textbooks is you should always try out small values of these parameters and see what really happens. For instance, if the algorithm took 2 parts, if it divided into 2 parts, then you can see that even the optimum will take 2 parts, right? Why is that so? Well, look at anything that landed in the second part. Okay, why was this interval put into the second part? Because it overlapped with something in the first part. Now, if you have 2 overlapping intervals, right? If you have two overlapping intervals, you better use two parts. Okay, so if you use two parts, you are through. Anybody else in this, working with the same input will use two parts. What about three parts? Okay. Well, what do you know? You know that if something was put into the third part, it must overlap with some interval in the first part and some interval in the second part. Let's look at this picture. Okay, so here, let's say I have an interval, right? So this was put into the third part, right? This interval was put into the third part, okay, which means there must be an interval that overlapped it, which was in the first part and second part, right? Now, what are the various things that can happen? Well, I can have, this was in the first part, and let's say this was in the second part. This is one scene, okay. What's the other scene that's possible? Let's say this was in the first part, okay, and let's say this was in the second part. Let's look at these two. Now, in this scenario, I claim that any other algorithm will also use three parts. Why is that? Well, at this line here, okay, when I look at this line here, all three of them intersect, right? So all three of them must be put in different locations, in different parts. Okay, so if it is this situation, then we are done. We are doing optimally as we should. Let's look at this situation. Now, in this situation, we cannot say the same thing, right? An optimum could have put these two into one part, in which case we are sunk. Well, can this happen? Can this situation happen? Okay, here's where we see we make progress, because remember, we've sorted these by starting times, right? So it looks like this cannot happen. The second scenario cannot happen. Okay, so focus on this. So in this scenario, it looks like this fellow starts after this, which means it should be considered afterwards, right? So this scenario cannot happen, and in fact, our ordering, okay, when we ordered, the ordering thing is to in fact get rid of these. So I guess, how would an algorithm designer go about doing this? Well, you'd say, okay, let me look at it in some order. Okay, intervals are looked at in some order. Now look for a proof. When you look for a proof, you see how you have to tune your algorithm so that the proof works, okay, and that's how the algorithm develops. So here we want to look at these intervals in some order, right, and put them into parts, put them into the first part that it can. We see that if there is a point where all of them intersect, then we are through. The only way this cannot happen is if I have a figure like that. So I have an interval and I have two intervals that do not intersect, okay, in two different parts. But if this happens, okay, one of them must have started after this third interval, right? One of them must have started after this interval that I am looking at right now. And then you go back and see, oh, can I get rid of this? Can I get rid of this in my proof? To get rid of this, now you notice that if you had looked at these intervals in increasing order of starting times, this case will not arise, okay? And so in trying to prove, you are actually refining your algorithm. You see that where your previous algorithm can go wrong, and you refine this algorithm to take care of this case, and you hopefully come up with this right algorithm. We were looking at the problem where you have a set of intervals, right? You have a set of intervals and you want to partition this set into a minimum number of parts, so that each part you have non-overlapping intervals. Okay, this is the problem, and the algorithm that we would like to consider is sort the intervals by the starting times. Look at them in increasing order of starting times, and when you look at an interval, put it into the first part that you can. Okay, the first interval goes into the first part. The second interval will go into a second part if it overlaps with the first one, and so on. So this is the algorithm, and in fact we would like to prove that this algorithm is optimum. Okay, so to prove this, well, we said supposing the algorithm produced k parts. Okay, we need to show that any algorithm will produce k parts, right? So let's look at this. Since there are k parts, okay, we said this, since there are k parts, let I be, let's say the first interval that was put into the kth part, the first interval, it does not matter, any interval you can pick from the kth part, but let us look at the first one, the interval that the algorithm put in the kth part. Okay, we would like to now argue that any algorithm will use k parts. Why is that? So here is I. Okay, this is my interval I. Well, if I take any other interval, okay, it has to start before I, right? Any other interval which has already been considered. Okay, so if I look at any other interval that has already been considered, it has to start before I. This much I know. I also know that in each of these parts, okay, in the parts 1, 2, 3, 4 up to k minus 1, first k minus 1 parts, there must be an interval which intersects with I. How does that look like? So let us say in the first part, how can the interval be? Well, it has to start before this, right, and it has to intersect this. So it has to end after this point. So it has to be something like this. It could, well, it could start here and it could end after I, that is fine, but it has to start before this point and it should end after this point. That is the crucial thing. So these intervals in the first part, second part, and so on that I overlapped with, okay, must start before this and end after this, which means this point must be common to all of these intervals, right. So all of these intervals overlap at this point and they must be put into different parts, okay, and you have k parts. There are k intervals which overlap at this point and hence they must be put into k different parts. So any algorithm will use k different parts. This is the idea. Okay, so let's write this down formally. So let I be the interval AB. Okay, in every part, well, this is 1 less than equal to every part P, say 1 less than equal to P less than equal to k minus 1. Okay, there is an interval which overlaps with I, because I was not put into this part, okay, which overlaps with I. Since I was not put into any of these parts, it was put into k, the part k. Well, now what can we say? This means this interval, there is an interval, let us say IP. So what can we say about IP? Well, IP starts before A and ends after A. Okay, it starts before A because I consider the intervals in increasing order of starting times, right, and it ends after A because it has to overlap with I. Okay, so this point A is in all of these intervals. Okay, so point A is in the intervals I1, I2 up to ik minus 1 and I. So, there are k intervals which has point A, so the optimum must have size k. That is the end of the proof. Okay, I am not writing that last sentence, just fill it in. The optimum must have size k because of this, because there are k intervals which has a point in all of them, right. So, the algorithm produces an optimum solution. Okay, that is what we wanted to prove. So, what I wanted to point out with this problem is that in the previous case we looked at them in increasing order of ending times, right, and in this case we look at them with increasing order of starting times. You could look at them with decreasing order of ending times and that will work. Okay, I will leave it to you again as an exercise. Okay, so I can look at these intervals in decreasing order of ending times and then do this partitioning, and that will also work. Okay, same proof, it's just the whole thing is similar. I guess you can see, because I can either look at the intervals from left to right or right to left, it really doesn't matter, right. So, things that work in one problem, the ordering which works in one problem may not work in some other problem, and this ordering of the input, the order in which you consider the input, is a crucial strategy in greedy algorithms. Okay. So, remember when I started I said there are three sort of paradigms, there are three techniques that run through all algorithm design, all these algorithms that we will design. One is induction, that is, if you can solve it for a smaller problem, how do you extend the solution to a bigger problem? The second is ordering the input. Okay, look at the input in the right order. And the third was storing old values. Okay, somehow store values which you may be reusing, right. In greedy strategy, this greedy strategy that we have looked at, you can see that there are two things, induction and ordering, which have so far played a crucial role, right. Okay. Yeah, so let me go back and tell you a bit more about this exchange trick. Then we will see a problem where couple of problems where this works beautifully. Okay. So, the exchange trick usually works when your algorithm looks like this. Okay, when the problem looks like this. So, you have a set of elements as input. Okay. You want a subset okay, as output, and usually you want the subset to satisfy some property. Okay. Okay, so this is how the problem looks like. Your input is a set of elements and you want a subset of this. Okay, so let us say that is this. Okay, you want a subset of this which satisfies some property as output. The first two problems were absolutely like this. Okay, what was your input initially? It was a tree. It was a set of vertices, and well, there are edges. Okay, there is input with some structure embedded in that. You want a subset. You want a subset of the vertex set, so that they are independent. You want an independent set as output, which is maximum in size. Okay, so the first problem had this property. The second problem also had this property, right? You had a set of intervals. You wanted a subset with maximum size, so that the intervals do not overlap. Okay, both these problems had this property. The third one was slightly different. You wanted to partition these intervals into many paths, right? Okay, so in the first and second, okay, fitted into this roughly this framework. Now, what is this exchange trick that I have been saying? Roughly, it is this. So, supposing you have a solution. Okay, supposing you have let us say a candidate Okay, these things are to help you design the algorithm. I am not giving you any I am not giving you algorithm as such, but telling you tips as to how to design this algorithm. Okay. So, your candidate algorithm solution is a subset, right. Okay. Now, the exchange trick is this: supposing you remove let us say an element, okay, x from this solution. So, call this T, okay, this is subset T from T, and add, let us say, y. The question you ask is, does the solution improve? Okay, we ask this question. So, if we can somehow identify when the solution improves, that could give us a clue as to how to design these algorithms, and that happened in the first two cases. So, let me sort of tell you, recall your jog your memory a bit. So, in the first case we said that if it did not have a leaf, then I can put this leaf in and I remove something else, right. The solution may improve. In the second case, I said that you could always put the interval that ended first into the solution and remove something else. That is how we sort of came up with that. We will now see examples where this works, this exchange trick works. Okay. Okay. The problem is this. It's actually a fairly simple problem, and even without this exchange trick, you should be able to come up with an algorithm, right. It's again from scheduling. So, you have a set of jobs. Okay, the input is a set of jobs with processing times okay, T1, T2 to Tn. There are n jobs and they have processing times T1, T2 up to Tn, right. There is a single processor. Okay, you have one processor and you want to schedule these. So, obviously, you will schedule them one by one. There is no preemption. In fact, in all our scheduling problems that we have taken up so far, there is no preemption. Okay, so you cannot stop a job in the middle. You allocate the process runs to completion, right. Yeah, so you want to schedule this on one processor, no preemption. Okay, so the output is a schedule on one processor. Okay, so there is no preemption. Well, and we want to minimize something. Okay, what do we want to minimize? We want to minimize the sum of the finishing times. Okay, schedule on one processor, no preemption, to minimize the sum of the finishing times. Okay. So, what do I mean by this? In fact, what do I mean by schedule? Schedule means I have to tell you in which order you put these jobs onto the processor. Okay. So, supposing I put them in order T1, T2, T3 up to Tn. This is the order in which I schedule them onto the processor. The finishing time of the first job is T1, right. The finishing time of the second job is T1 plus T2, right. The finishing time of the third job is T1 plus T2 plus T3, okay. The ith job is T1 plus T2 up to Ti, right. This is the finishing time of the ith job. I want to minimize the sum of the finishing times, okay. So, each job has a finishing time. I add up all finishing times and I want to minimize the sum of the finishing times. This is the problem. So if you in fact just look at you look at this sum. Okay, what is this? Okay, so just take a minute. So the first finishing time F1 is T1, F2 is T1 plus T2, so on. Fi, the ith finishing time is T1 plus T2 plus 2 Ti, right? Now what is sigma Fi, Fj, let us say j equals 1 to n. This is what I want to minimize. Well, it's T1 plus T1 plus T2 and so on up to the last one, right? Fn is T1 plus T2 and so on plus Tn. It is the sum, it is this sum. It's, if you sort of look at this sum, it's nothing but n times T1 plus n minus 1 times T2 and so on up to plus Tn is some ones. Okay. And when you look at this sum, you immediately realize that I better have the smallest job here, sitting here, right? T1 should be minimum among the T's, T2 should be the next minimum and so on, and Tn is the maximum time. Okay, it's when you just look at this, you see that's the way it should be, and in fact the proof is also obvious, right? And that's the algorithm. So you just sort of sort the jobs by increasing times, right? And that's what it should be, just by looking at it. So that is a very simple algorithm for this problem. We'll look at this problem again just to sort of push in a point when we start next time, and then we'll look at slightly more complicated problems from the greedy perspective. Okay.